Momo and Good Morning Coffee. Okay. I don't know why the stream is not going to. I'm gonna have to learn to say the red platform. Good morning to me. I don't know why. Okay, now chat should show up. Hopefully. But for some reason, yeah. I'm trying to send it and it's just not going there. The setup is the same. I didn't change anything. And I'm like, okay, not much I can do about it. Yesterday was like a not possible to stream day for some reason. I again didn't change anything about my setup and stuff, but life happens sometimes. And I'm hoping today will be fine. It looks fine enough. It was only the clock app had weird rules about mentioning the other. It is, and my plan is to use it someday. I got banned last week for saying YouTube and Twitch. So my plan is to start learning to say the red platform and the purple platform so that yeah. So that when I do start rejoining, I don't get kicked out again, because I'm sure it's not going to be good on my resume. Because I tried streaming Thursday on the clock app TikTok, but I think 5 minutes in I was banned from streaming. So I'm gonna try and be I'm gonna try and be a good citizen. Yes. So the plan for today, the agenda is to start easing into my new plan of learning math. If the internet does not hurt me too much for the time being, it looks not great and it is deteriorating. Can I close this while having this? Is that possible? Can I have a pop-out chat? What happened to the chat? Where's the chat? I don't think that is possible, is it? Here's chat. So if chat is here, and if I close this, oh, chat remains. That's lovely. Great. So now, that should be fine. That's what I think. That's what I still think, that it shows me based on my geographical location. My goal is that oh god, I keep hitting the mic with my headphone. My goal is that everybody in my region is not interested in what I'm doing and see where we go from there. To get rejected by everybody is my goal. Yeah. So let's go to the other scene of showing my screen. Ta-da! So this is apparently my profile. When you go to khanacademy.com, it redirects you to your profile. But if you go to the explore part, the math stuff, the math things, I am rather interested in. Remember an American streaming from Japan who found it useless with a Japanese account because his audience were primarily American. Seems like it. I guess it's I'm sure it works for them and they're doing that for a reason, right? Promoting people in their own geographical region. I'm sure they have a reason behind it. I'm gonna skip pre-K to 8th grade and start looking at what the high school to college part has, and you can see it starts with, I can't press this and have it go to my to a place with all of this. I can see it here. It starts with Algebra 1 and then Geometry and so on. And I think I have, I have Algebra 1. I think I selected some stuff when I first made the account. Probably works for most users. Yep, basically. So I have Algebra 1 here, which is called Zebr in Arabic. Al-Zebr? Zebr? Do I have geometry? Do I want geometry? Anyway, see, yeah, it's like add courses. Which courses would you like to see? Here's geometry. Let me see the maths, because my plan is to check the ones that are relevant. I think I just checked those for funsies, honestly. I'm just gonna follow this here and start with Algebra 1. Let's go. Do I not have pen and paper with me? Because math equals pen and paper to me. Okay. I don't know much about Khan Academy. It's my first time using it, if you can believe that. I don't know if there are any like so this is progress. Mastered, proficient, familiar, attempted, not started, quiz and tests. So you have quizzes and tests. I don't know. I don't think anything is behind a paywall, right? Okay, get started. Let's do this. Yeep. All right. I'm doing this. Should I zoom in just a bit? About this unit. Why did humans invent algebra in the first place? Who invented algebra? If I Google it, and if I go here, I know it was in here, but who? Do you have a history? Ancient Egypt, okay. But the word zebr comes from somewhere. Khwarizmi. There it is. That's the name I wanted to see. Yeah. Okay. I think he wrote the book on math. 825. Persian mathematician Al-Khwarizmi published the compendious book on calculation by completion and balancing. Yay. And I know his face, right? Well, yeah, of course I know his face. Muhammad ibn Musa al-Khwarizmi. Awesome. During the Islamic Golden Age. Okay, I'm gonna stop being gushing about the history of this region. Anyway, let's look at the history and we're gonna look at the history, beauty of algebra, and review some fundamental ideas and tools we'll use throughout the course. Yeah. I guess my relationship with mathematics, is I have thought of myself someone who's good at it up until like finishing high school, and then for some reason during my undergraduate years, I just failed anything that had to do with maths, and I'm guessing it's because I stopped trying. Maybe, I hope. So my plan here and now is just to fall in love with math again, and to just like be able to use it during intro to ML related stuff. That's my actual goal, but also to not see myself as someone who's bad at it, to see myself as someone who likes math, you know? So this is for, I'm guessing this PDF is for teachers and not learners. What happened? Overview and history. Is there a get started page, or do I just click this and we go there? Okay, unit guide. It's like a cheat sheet-ish. Oh, we have a video. This is Khwarizmi's book, right? You should be able to hear sound. If you don't, let me know.
What I want to do in this video is think about the origins of algebra. The origins of algebra. And the word, especially in association with the ideas that algebra now represents, comes from this book, or actually this is a page of the book right over there. The English translation for the title of this book is The Compendious Book on Calculation by Completion and Balancing. And it was written by a Persian mathematician who lived in Baghdad I
Sorry.
believe it was in
Yes, of course they lived in Baghdad in the sorry. I get excited about the beautiful history of this region because we had I always forget House of Wisdom, right? That's the name of the university. That was a place for scientists to just be and just anyway. Yes. I promise not to scream anymore. It's just I heard the word Baghdad and it made me it at the same time makes my heart swell because I'm happy about it, but also it makes me so sad. Because now if you hear the word Baghdad, you think, oh, Iraq war, obviously, what else? Yeah. Anyway.
Persian mathematician who lived in Baghdad I believe it was in the 8th or 9th century. I believe it was actually 820 AD when he wrote this book, AD. And algebra is the Arabic word that here's the title that he gave to it, which is the Arabic title. Algebra means restoration or completion.
Jabr means completion. الكتاب المختصر okay في صحاب الجبر. Why جبر? I read it as جبر. مقابلة. Does مقابلة mean balancing? It says what? Oh God. Anyway. I think first thing comes to my mind is just capital cities of the world. Thank you. I appreciate that. It's just a city. Don't think too far into it.
Restoration or completion. And he associated it in his book with a very specific operation, really taking something from one side of an equation to another side of an equation. But we can actually see it right over here. And I don't know Arabic, but I actually do know some languages that seems to have borrowed a little bit from Arabic, or maybe it went the other way around. But this says Al-Kitab, and I know just enough Urdu and Hindi to understand a good Indian movie. But Al-Kitab, kitab means book. So this part is book.
Okay, he's gonna read it.
Book. Al-Muqtazar, I think that means
Mukhtasar. Is it a mukhtasar, which means like shortened?
Compendious, because I don't know the word for compendious, and that seems like that. Fi hisab. Hisab means calculation in Hindi or Urdu, so this is calculation. Al-Jabr. This is the root. This is the famous algebra. This is where it shows up. So this is for completion. You could view that as completion. And then wa al-muqabla, and that means essentially balancing, completion and balance.
To me, muqabala means like something compared to, which like to me it means comparing, but I suppose it can mean balancing. I could be wrong. Do not trust my my translations.
Balancing. So if we wanted to translate, and I know this isn't a video on translating Arabic, but the book, I guess this is saying compendious on calculation and calculation by completion and balancing is the rough translation right over there. But that is the source of the word algebra. And this is a very, very, very important book, not just because it was the first use of the word algebra, but many people view this book as the first time that algebra took a lot of its took on many of its modern ideas of balancing an equation, the abstract problem itself, not trying to do one-off problems here or there. But Al-Khwarizmi was not the first person. And just to get an idea of where all of this is happening, so he was hanging out in Baghdad. So this part of the world shows up a lot in the history of algebra.
Baghdad should be here, where the two water things meet. What was I thinking? I wanted to say something and then I forgot. He's not the first person to do this, but he's like the one who did the collection, right?
But he was hanging out right there in around the 8th or 9th century. So let me draw a little timeline here.
Should be during Harun Rashid time, because he gave so much to House of Wisdom, of course, like to science. And he's like the leader person who he probably wasn't the kindest person as far as my memory serves, but yeah, Abbasi Caliphate, but like 820, is it during Harun Rashid time, or do I wait. Where are caliphate names? And why am I 820? Where is it? Why are we, where is there time that's missing? Weird. Okay, let me go back, click Islamic Golden Age, and see what are the names of the caliphate persons. Ooh. See, some figures of the Islamic Golden Age: Khwarizmi, Biruni, Ibn al-Nafis, oh wow, that's not even an Arabic name, right? Am I wrong? Oh, Ibn Sina. Okay. Yeah. Oh, look at that, Ibn Farnas. Okay, again, I should not do this, but I just want to see Harun al-Rashid. There we go. Okay, that's good. And he was the person during that time, yeah, who cared about science and knowledge. Nice. This is not supposed to be a history lesson. Oh god, I didn't see, I'm so engrossed, I didn't notice this. This is supposed to be a math lesson. I don't know how slow I will go. Apparently I am enjoying the learning part
here, just so we can appreciate everything. So that is timeline, and then whether or not you are religious, most of our modern dates are dependent on the birth of Jesus. So I will put, so that is right there. We'll put a cross over there to signify that. When we want to be non-religious, we say Common Era, before the Common Era. When we want to be religious, we say AD, which means in the year of our Lord, Anno, I don't know the Latin, Anno Domini, I believe, year of our Lord. And then when we want to, and in the religious context,
BC?
Instead of saying before Common Era, we say before Christ, BC. But either way. So this is 1000 in the Common Era. This is 2000 in the Common Era. And obviously we are sitting, at least when I'm making this video, I'm sitting right about there. And then this is 1000 before the Common Era. And this is 2000 before the Common Era. So the first traces, and I'm skipping out, and really it's just what we can find. I'm sure if we were able to dig more, we might be able to find other evidence of different civilizations and different people stumbling on many of the ideas in algebra. But our first records of people really exploring the ideas that are hit upon in algebra come from ancient Babylon, around 2000 years.
I know ancient Babylons didn't expect a girl to stream and say, I'm proud of them and that I'm from the same region as them. But hey, I'm also from the same region as I think. Well, I mean, region is a forgiving word. I think Babylonians were from here, right? Mesopotamia. My history is shaky.
Before the Common Era, before Christ. So right around right around there. There are stone tablets where it looks like people were exploring some of the fundamental ideas of algebra. They weren't using the same symbols, they weren't using the same ways of representing the numbers, but it was algebra that they were working on. And that was, once again, in this part of the world. Babylon was
Yes,
right
I
about,
told you.
right about there. And Babylon, it's kind of kept the tradition of Sumeria. This whole region was called Mesopotamia, Greek for between two rivers.
I'm from, oh yeah, between the two rivers. I'm from the two rivers, guys. I'll stop.
But that's the first traces of people that we know of where people were starting to do what we would call real algebra. And then you fast forward, and I'm sure we're missing, and I'm sure even our historians don't know all of the different instances of people using algebra. But kind of the major contributions to algebra, we saw it here in Babylon 2,000 years ago. And then if we fast forward to about 200 to 300 AD, so right over there, you have a Greek gentleman who lived in Alexandria. So this is Greece right over here, but he lived in Alexandria, which at the time was part of the Roman Empire. So Alexandria is right over here. And he was a gentleman by the name of Diophantus.
Yeah, Alexandria we call Al-Iskandariya, which is in Egypt, right? I'm gonna snooze this ad, but if an ad comes along, I'm gonna not play anything that is information, okay? I'm gonna take an actual ad-ish break if an actual ad comes along. Let me know, okay? In the chat. I don't want you to miss out on this cool information.
Or Diophantus, or I don't know how to pronounce it. Diophantus, and he is sometimes credited with being the father of algebra, and it's debatable whether it's Diophantus or whether it's Al-Khwarizmi. Al-Khwarizmi kind of started using these terms of balancing equations and talking about math in a pure way, while Diophantus was more focused on particular problems, and both of them were kind of beat to the punch by the Babylonians, although they all did contribute in their own way. It's not like they were just copying what the Babylonians did. They had their own unique contributions to what we now consider algebra, but many, especially Western historians, associate Diophantus as the father of algebra, and now Al-Khwarizmi.
I mean, can't they both be grandparents of algebra?
Is sometimes what other people would argue as the father of algebra.
I'm the other people. Okay.
So he made significant contributions. Then if you go to 600 AD, so if you go to about 600 AD, another famous mathematician in the history of algebra was Brahmagupta in India.
Ooh.
Brahmagupta in India. So obviously, and actually I don't know where in India he lived. I should look that up, but roughly in that part of the world. And he also made significant contributions. And then of course you have Al-Khwarizmi, who shows up right there. Al-Khwarizmi, and he's the gentleman that definitely we credit with the name algebra. Comes from Arabic for restoration, and some people also consider him to be, if not the father of algebra, although some people say he is the father. He is one of the fathers of algebra because he really started to think about algebra in the abstract sense, devoid of some specific problems, and a lot of the way that a modern mathematician would start to think about the field.
Nice. Okay, so that was origins and history. Do we have yeah, I guess everything that was read here we heard. There are no questions to be asked, so we just go next. Where should the next button be? Do we have a next button? Did I zoom in too much for me? Yes, I did zoom in too much. Here's our next button. Abstract-ness. What is abstract-ness?
You'll hear me use the word abstract a lot, so I thought I would actually give you an attempt at a definition, or maybe even more important, an intuition of what abstract means. An abstract, it can be an adjective. You can have an abstract idea. You can have abstract art, or it can be a verb. You can abstract something, abstract the idea from some other idea. And you can even have it as a noun. You can have an abstract, and it tends to, when you use it as a noun, the one that I tend tend to associate is the abstract of a research paper, which is kind of
Oh, yeah.
distills the essence of the research paper. It's kind of a summary of that paper. And the one thing you're going to see, regardless of what context you use the word abstract, there's this kind of notion of taking the essence of a real world, of a real world object, whether you use it as a noun, an adjective, or a verb. So over here we have our real world. We have our real world. And then over here you have your world of, you have ideas and concepts. And the general idea behind abstraction or abstracting something is you're taking it away from the particular concrete
You can abstract in the digital circus? Do I understand what that is? I mean, I don't know what that is, but I like the fact that he is defining every word, because this is a high school level math. Oh, I don't know that. Hey, I can check that out later. This is supposed to be high school level stuff, and I like the defining parts. Oh, I have seen, I have seen images, but not gone into them further. All right.
Real world, and you're going more in the direction of ideas and concepts. And probably for me, one of the most tangible ways of thinking about abstraction, which is kind of a contradiction in itself to think of abstraction in a tangible way, is things like geometric shapes. So if I were to tell you find me some cubes, you might point to a Borg vessel right over there. A Borg vessel. You might point to maybe a pair of dice. So let me draw the pair of dice. If you are looking for cubes. So you might point to a pair of dice that looks something like that. You might point to a Rubik's Cube, anything that you could find. There might be a building that looks like a cube. There might be a building that looks like a cube. Or maybe there's a box in your house that is a cube. But in your mind, you have a general idea of what a cube is. You're like, well, I know a cube when I see one. And that general idea is essentially distilling the concept, the idea of what a cube is. All of these things are very different. This is some plastic thing that I can hold in my hand. These are these little white things, and they're not even, geometrically even close to being perfect. They have these little divots on the side right over there. This is a large Borg vessel that, it doesn't even exist yet. It's not, obviously it's a fictional thing. But they all have this cubeness to them, and this is one of the fun things of geometry, is to really distill the essence of these real world shapes. And we do have a definition in geometry, which is an object like this. I guess you could have an object
6 sides
like this, where every side has the exact same length. So if this is length 1, then that would be length 1. That is length 1. But it doesn't have to be. Whatever the length this side is in this dimension, then in this dimension is going to be that length, and in that dimension it's going to be in that length. And I'm not giving you the rigorous geometric definition, but I'm just trying to highlight that there is a pure idea of what a cube is. And in the real world, there is nothing that is actually a perfect cube.
Probably.
If you were to get really, really close to these die, if you were to really try to measure exactly their measurements, they won't be exactly the same measurement. But the abstract idea of a cube, this is completely the same length as this, and actually this, and all of the edges are going to have the...
Yeah, it doesn't exist yet. It could happen. We are hopeful here.
Exact same length. So this is going from the concrete, the specific, from the real world, if you consider the 24th or 25th century the real world, to going to the idea behind it, the general idea. And you've probably also heard the word abstract in terms of art, like abstract art. So this is abstract art. And it's the same general idea. If you look it up on a dictionary, you're going to find 20 definitions of the word abstract. But it's all essentially trying to say the same thing. Abstract art is art that is not focused on trying to paint reality the exact way that reality exists. If you look at kind of a lot of Renaissance art, they're skilled at painting figures exactly how they look in the real world. But the abstract artists, sometimes they're not even trying to even represent anything that's in the real world. They're trying to represent a raw idea, or they're trying to represent a raw expression of color and form and texture. And this is a Jackson Pollock painting right over here, and I pronounce many things wrong. This was taken by our own Stephen Zucker, art historian. And as you can see, it's not clear. Jackson Pollock is not trying to paint, a dog or a horse or anything like that. He is painting something that is devoid. It's completely independent of anything that we actually see in physical reality.
Cool.
And the word abstraction, it doesn't just apply to pure geometry and art. It applies to almost everything that we do on a daily basis. When we even talk about things, when we even use words or use symbols, we're essentially abstracting away. We're abstracting the essence of something that actually exists in physical reality. So if I use the word dog, it's a set of symbols. This set of symbols represents something in our minds that we associate with dog. We have in our minds kind of the
So even like saying language is a form of abstraction.
Qualities of what a dog actually is. It has 4 legs and floppy ears, and you enjoy petting it, and they're man's, or I guess people's, best friend. You imagine this thing called a dog, and it has the essence of dogness, even though when you actually look at dogs in the real world, they look very, very, very different types of animals. Whether you're looking at a Great Dane or a
Chihuahua,
or a kind of a super small poodle, but we recognize there's an essence of those particulars that we can abstract away and say this is a dog. And then we abstract it even more by representing these letter symbols that tend to conjure up this image, even when we write something as simple as a number. So if I write the number 5, we use it so frequently that to us, a number 5 seems kind of like a concrete thing, but it's so abstract. It's just a quantity of things. I could have symbolized it like that. I could have symbolized 5 like that. I could have symbolized 5 in Roman numerals like that. I can symbolize it like that. And in all of these cases, it's the idea of a quantity of 5 things. 5, if we were, you could say, point me to a 5, someone would probably point you to something like that, but they're still pointing you to the symbol of 5. But it's still
or you
a very,
can hold
very
up your hand.
Abstract idea. So hopefully this gives you an appreciation for what abstract means. As you can tell, it's kind of a, for lack of a better word,
Abstract.
It's kind of an abstract idea. Not
Nice.
to be too cute about that.
So I think we are in an ad break. I'm just gonna press next and check if we are in an ad break. Should have checked sooner. I don't know, because I did see saying ad is coming up. So let's just wait 1 minute and we shall continue. Yes, so let's do the thing where you're like, how much more do I have left? Oh, actually, the guide should tell us that. Oh, Unit 1, Foundations. Where's the history part that we were just looking at? Because all of this is useful. I mean, there we go. Overview and history. Is that what we were looking at? Is this overview and history? So this is lesson 1. How many lessons are there in total? 26. Only 6. Now I see saying when the ad breaks ends. Oh, cool. Okay, so you didn't get an ad. Just in case. I see saying ad break ends in 40 seconds. So we're gonna continue playing that in 40 seconds. So we see this one has 1, 2, 3, 4, 5, 6. If Unit 1, we were just here. Okay, now I see where we are. So each of them has like a 5 thingy, 5 lessons inside. I don't want to take the quizzes or tests. I don't mind just going through it normally. Yeah. So algebra is 16 units. Each of them have 5 lessons. I'm just trying to see how long it could take me. Probably too long. Because like it's not an exhausting thing. So I'm just trying to think about my my schedule. What I want my schedule to be. Because I feel like we'll see. We'll see. I remember when I first saw algebra in school, I was confused because it was a little like variables in programming, but not. Wait, did you know about programming before you knew about algebra, or vice versa? Because I think math comes first. Like I didn't start programming until I was 18, so like until I got into a computer science class. But honestly, personally, I prefer programmer math than abstract math. Like for me, obviously programming languages are levels of abstraction, but yeah, I prefer learning math through programming because that feels easier for me. Like it's something that I can understand. Alrighty, we are going to play the video about the beauty of algebra. Let's do this.
Before we get into the meat of algebra, I wanted to give you a quote from one of the greatest minds in human history, Galileo Galilei, because I think this quote encapsulates the true point of algebra and really mathematics in general. He said, "Philosophy is written in that great book which ever lies before our eyes. I mean the universe. But we cannot understand it if we do not first learn the language and grasp the symbols in which it is written. This book is written in the mathematical language, without which one wanders in vain through a dark labyrinth." So very dramatic, but very deep. And this really is the point of mathematics. And what we'll see as we start.
Mathematics is the language of the universe. Found a programming manual for an old computer I got for $5 at a garage sale and played with that as a kid. Aw, that's lovely. Well, that's cool. We have we each have our own way of learning about. It came with it. Cool. I mean, we've probably had a few programming or guide style books that I have not even opened. Yeah. I don't think I ventured too far learning on my learning path. I was like, school is school, and that's my learning. Everything else was like, I'm watching a movie, I'm enjoying entertainment, or like reading kids' books. Yeah, that's as far as I went.
Getting deeper into algebra is that we're going to start abstracting things, and we're going to start getting to core ideas that start explaining really how the universe is structured. Sure, these ideas can be applied to things like economics and finance and physics and chemistry, but at their core, they're the same idea, and so they're even more fundamental, more pure than any one of those applications. And to see what I mean by getting down to the root idea, let's go with we started with the very grand, the philosophy of the universe is written in mathematics. But let's start with a very concrete, simple idea. But we'll keep abstracting, and we'll see how the same idea connects across many domains in our universe. So let's just say we're at the store, and we're going to buy something, and there's a sale. The sale says that it is 30% off. 30% off. And I'm interested, I don't shop at my too fancy stores. So let's say I'm interested in a pair of pants, and the pair of pants before the sale even is about $20. And that is about how much I spend on my pants. So I'm interested in a $20 pair of pants, but it's even better. There's a 30% there's a 30% off sale on these pants. Well, how would I think about how much I'm going to get off of that $20? And this isn't algebra yet. This is something that you've probably had exposure to. You would multiply the 30% times the $20. So you would say your discount is equal to, you could write it as 30%.
I love calculating discounts.
Times $20. I'll do the $20 in purple. Or you could write it, if you wanted to write this as a decimal, you could write this as 0.30 times $20. And if you were to do the math, you would get $6. So nothing new over there. But what if I want to generalize it a little bit? That's the discount on this particular pair of pants. But what if I wanted to know the discount on anything in the store? Well, then I could say, well, let x be the price. Let me do this in a different color. So I'm just going to make a symbol. Let x be the price of the product I want to buy. Price, the non-discount price.
Yeah, it's just fun seeing something discounted. Like, even if I don't want to buy it, I'm like, okay, but how much would I save? Yeah, and my brain for this 30% of the $20 went, well, 30% of a $10 is 3, so for 20, it's 3 times 2. That's how my brain went. But not everything is that easy.
Non-discount price of the product in the store. So now all of a sudden we can say that our discount is equal to 30% times x.
Yep.
30% times x. Or if we wanted to write it as a decimal, we could write, if we wanted to write 30% as a decimal, we could write 0.30 times x. Now this is interesting. Now you give me the price of any product in the store, and I can substitute it in for x, and then I can essentially multiply 0.3 times that, and I would get the discount. So now we're starting to, very slowly, we're starting to get into the abstraction of algebra. And we'll see that these will get much more nuanced and deep, and frankly, more beautiful as we start studying more and more kind of algebraic ideas. But we aren't done here. We can abstract this even more. Over here, we've said we've generalized this for any product. We're not just saying for this $20 product. If there's a $10 product, we can put that $10 product in here for x, and then we would say 0.30 times 10, and the discount would be $3. It might be a $100 project, then the discount would be $30. But let's generalize even more. Let's say, well, what is the discount for any given sale when the sale is a certain percentage? So now we can say that the discount, let me define a variable. So let's let m equal, or I'll say p, just so.
I'm shopping for an emergency PSU today. After sudden hardware failure, seeing discounts is not enough to improve my feelings on it. It would be nice if they gave it for free. But then you'd be like, okay, why are you giving it for free? Is there something wrong with it? Because even discounts. Okay, thank you. I wasn't sure what was a PSU. Power supply unit. Wait, does the chat not work on this screen? Why can't I see chat? Oh, it works here. But not here. Did I mess something up? Oops, I didn't notice that. Thank you. Yeah, same. I probably need to go to the black void to fix it, because I have my layers of scenes. But it's literally the same. Well, it's not exactly the same thing. Okay, let me try and test. It's the same thing, but with different CSS. Test for me. Huh. Let's go to the black void. And we're out of the black void. It's a API thingy, right? And if I do another test, Okay. It comes up. Anyway, apparently it requires further testing. For the time being, I could just remove the CSS that I added to make it different visually. Let me try. No, I don't think it's a layer order because I'm in the black void. It should come up because like it's the place. Huh. That's weird. I don't think so. It's the toppest layer right now. Here. Same here. Gone back. See? Interesting. Well, what is a stream if it's not, as the kids say, scuffed? If it doesn't have issues, you know? I'm sure Galileo Galilei had his difficulties in life as well. This is supposed to be sarcastic because his life was actually really difficult.
Makes sense. P is equal to the percentage off. Percentage off. Now what can we do? Well, now we can say that the discount is equal to the percentage off. In these other examples, we were picking 30%, but we can say now it's P. It's the percentage off. It's P. That's the percentage off times the product in question, times the price, the non-discount price of the product in question. Well, that was X. The discount is equal to P times X. Now, this is really interesting. Now we have a general way of calculating a discount for any given percentage off and any given product X. And we didn't have to use these words and these letters. We could have said, let y equal the discount. Let y is equal to the discount. Then we could have written the same underlying idea. Instead of writing discount, we could have written y is equal to the percentage off, is equal to the percentage off P times the non-discount price of the product times X. And you could have defined these letters any way you wanted. Instead of writing y there, you could have written a Greek letter, or you could have written any symbol there, as long as you can keep track of that symbol represents the actual dollar discount.
Yes.
But now things get really interesting, because we can use this type of a relationship, which is an equation. You're equating y to this right over here. That's why we call it an equation. This can be used for things that are completely unrelated to the discount price at the store over here. You might have, so in physics, you'll see that force is equal to mass times acceleration. The letters are different, but these are fundamentally the same idea. We could have let y is equal to force. We could let y is equal to force, and m is equal to, or mass is equal to p. So let me write p is equal to mass. And this wouldn't be an intuitive.
So basically what he's saying is that mass is a discount.
Way to define it, but I want to show you that this is the same idea, the same relationship, but it's being applied to two completely different things. And we could say x is equal to acceleration. We could say x is equal to acceleration. Well, then the famous force is equal to mass times acceleration can be rewritten, and it's really the same exact idea as y, which we've defined as force, can be equal to mass, which we're going to use the symbol p, which is equal to p times acceleration. We're just going to happen to use the letter x here, times x. Well, this is the exact same equation. This is the exact same equation. We can see that we can take this equation, and it can apply to things in economics, or it can apply to things in finance. Or it can apply to things in computer science or logic or electrical engineering or anything, accounting. I mean, there's an infinite number of applications.
My most use of math is, I think, I mean, obviously money, but like changing numbers, number bases, like saying for school, I got like 7 out of 10. Okay, but what is that if it was out of 20 or if it was out of 100? And 10 and 100 is easy to convert, but if it has a different base, then I don't know if base is the correct word, but then converting that, like this exam was over like 60 because the other 40 is from a different practical exam and all of that, and you're like, okay, but what would it be if it was 100? So that's the math I like to do.
Of this one equation. And what's neat about mathematics and what's neat about algebra in particular is we can focus on this abstraction. We can focus on the abstract here, and we can manipulate the abstract here. And what we discover from these ideas, from these manipulations, can then go and be reapplied to all of these other applications, to all of them. And even neater, it's kind of telling us the true structure of the universe if you were to strip away all of these human definitions and all of these human applications. So for example,
Everything is X. That's it. You can abstract everything with everything.
We could say, look, if y is equal to p times x, so literally if someone said, hey, this is y, and someone says on the other hand, they say, I have p times x, I could say, well, you have the same thing in both of your hands. And if you were to divide one of them by a number, and if you wanted them to still be equal, you would divide the other one by that number. So for example, let's say we know that y is equal to p times x. What if you wanted to have them both be equal, and you say, well, what is y divided by x is going to be equal to? Well, y was equal to p times x, so y divided by x is going to be the same thing as p times x divided by x. But now this is interesting.
Y divided by
p.
p
Times x divided by x. Well, if you multiply by something and then divide by that something.
Oh, right. Yeah, I mean, you can say p equals.
It's just the same. You're going to get your original number. If you multiply by 5 and divide by 5, you're just going to start with p or whatever this number is. So those would cancel out. But we were able to manipulate the abstraction here and get y over x is equal to p. And let me make that x green. Y over x is equal to p. And now this has implications. This has implications for every one of these ideas. One is telling us a fundamental truth about the universe, almost devoid of any of these applications. But now we can go and take them back to any place that we applied. And what the really interesting thing is we're going to find there are an infinite number of applications. And we don't even know, frankly, most of them. We're going to discover new ones for them in 1,000 years. And so hopefully this gives you a sense for why Galileo said what he said about really mathematics is really the language with which we can understand the philosophy of the universe. And that's why people tell us that if a completely alien life form were to ever contact humans, mathematics would probably be our first common ground, the place that we can start to form a basis that we can start to communicate from.
Yes, and if anyone's read the book Hail Mary, Project Hail Mary, I think that's spoilers, but not really. I'm not gonna spoil it. But yeah, same. Basically. Oh, hey, we see the face of the guy who was talking. Cool. I'm curious when these videos were created because they look new, and also it's written head of AI, meaning it's probably new. And chief innovation person, probably.
It's all about solving problems. It's not about, like maybe in previous years you've done multiplication table memorization. It's not like memorizing how to solve problems. It's learning the tools of how to solve problems and then using them and building them up in creative ways. So it's kind of like, it really does remind me of art, because if you are doing like a painting or something, you have like a specific tools about like maybe paintbrushes or different techniques you can use to create something bigger. So I feel like algebra is really all about combining things that you already know how to do into something bigger.
So the word algebra comes from the Arabic word al-jabr, that literally translates to reunion of broken parts. This breaking apart of mathematical representations and putting it back together in the form of balanced equations is the essence of algebra. And the beautiful thing is that this balancing and solving of equations can be done in many different ways, which is where creativity comes in.
Nice. That was cute. Just like a break. And this person was not the person who was talking. My brain read it wrong. I saw Saad and I thought the other person's name was Saad, but I guess I'm wrong. Oh, Sal. I saw an S and a Khan, and I'm sorry. I messed up. So, okay, coordinate plane, the X and Y axis. Cool. Oh, geometry. Then we absolutely need geometry. See, I needed to see it to believe it, but obviously, like stuff like gradient descent is all geometry, right? So we absolutely need geometry. All right, let's think and be. I think, therefore I am. We're gonna think and be.
This right here is a picture of René Descartes. Once again, one of the great minds in both math and philosophy. And I think you're seeing a little bit of a trend here that the great philosophers were also great.
It's not me. The voice is lower this time, right?
Mathematicians and vice versa. And he was somewhat of a contemporary of Galileo. He was 32 years younger, although he died shortly after Galileo died. This guy died at a much younger age. Galileo was well into his 70s. Descartes died at this is only at 54 years old. And he's probably most known in popular culture for this quote right over here, a very philosophical quote. I think, therefore I am. But I also wanted to throw in, and this isn't that related to algebra, but I just thought it was a really neat quote, probably his least famous quote, this one right over here. And I like it just because it's very practical. It makes you realize that these great minds, these pillars of philosophy and mathematics, at the end of the day, they really were just human beings. And he said, you just keep pushing. You just keep pushing. I made every mistake that could be made, but I just kept pushing, which
That's some good advice.
I think is very, very good life advice. Now,
I want to say Renee. I can call him Renee, right? Sometimes I feel like I'm pushing too hard and there's nothing on the other side, and I feel like life is weird. It's like, what am I pushing for? But also, I want to do stuff. You know, I want to continue. I don't want to sit still. So this is lovely advice to think that someone from hundreds of years ago. It's like, for me, it looks like a mix of saying I've made every mistake that can be made. Thinking yourself as someone who's not enough, but also who can do more, right?
Did many things in philosophy and mathematics, but the reason why I'm including him here as we build our foundations of algebra is that he is the individual most responsible for a very strong connection between algebra and geometry. So on the left over here, you have the world of algebra. And we've discussed it a little bit. You have equations that deal with symbols, and these symbols are essentially, they can take on values. So you could have something like y is equal to 2x, y is equal to 2x minus 1. This gives us a relationship between whatever x is and whatever y is. And we can even set up a table here and pick values for x and see what the values of y would be. And I could just pick random values for x and then figure out what y is. But I'll pick relatively straightforward values just so that the math doesn't get too complicated. So for example, if x is negative 2, then y is going to be 2 times negative 2 minus 1. 2 times negative 2 minus 1, which is negative 4 minus 1, which is negative 5. If x is negative 1, then y is going to be 2 times negative 1, 2 times negative 1 minus 1, which is equal to, this is negative 2 minus 1, which is negative 3. If x is equal to 0, then y is going to be 2 times 0 minus 1. 2 times 0 is 0 minus 1 is just negative 1. I'll do a couple more. If x is 1, and I could have picked any values here. I could have said, well, what happens if x is the negative square root of 2? Or what happens if x
No.
is negative 5 halves? Or positive 6 sevenths? But I'm just picking these numbers because it makes the math a lot easier when I try to figure out what y is going to be. But when x is 1, y is going to be 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. And I'll do one more. I'll do one more in a color that I have not used yet. Let's see, this purple. If x is 2, then y is going to be 2 times 2. Now our x is 2 minus 1. Minus 1. So that is 4 minus 1 is equal to 3. So fair enough. I just kind of sampled this relationship. I said, okay, this describes a general relationship between a variable y and a variable x. And then I just made it a little bit more concrete. I said, okay, well then if x is one of these for each of these values of x, what would be the corresponding value of y? And what Descartes realized is that you could visualize this. One, you could visualize these individual points, but that could also help you in general to visualize this relationship.
Yes.
And so what he essentially did is he bridged the world.
I think Descartes would have loved to use things like matplotlib and stuff like that. I think he would love using the visualization tools we have. I feel sad in my heart to know that he had to visualize everything with his hands, but I'm sure he didn't mind it.
Of this kind of very abstract symbolic algebra, and that and geometry, which was concerned with shapes and sizes and angles. So over here you have the world of geometry. And obviously there are people in history, maybe many people who history may have forgotten, who might have dabbled in this. But before Descartes, it's generally viewed that geometry was Euclidean geometry. And that's essentially the geometry that you study in a geometry class in 8th or 9th grade or 10th grade in a traditional high school curriculum. And that's the geometry of studying the relationships between triangles and their angles and the relationships between circles, and you have radii, and then you have triangles inscribed in circles and all the rest. And we go into some depth in that in the geometry playlist. But Descartes says, well,
so when I saw geometry, this is what I was thinking. I was like, I don't need to calculate areas and angles and circumferences and stuff like that, but this geometry I need.
I think I can represent this visually the same way that Euclid was studying these triangles and these circles. He said, well, why don't I, if we view a piece of paper, if we think about a two-dimensional plane, you could view a piece of paper as kind of a section of a two-dimensional plane. We call it 2 dimensions because there's 2 directions that you could go in. There's the up-down direction. That's one direction. So let me draw that. I'll do it in blue because we're trying to visualize things. So I'll do it in the geometry color. So you have the up-down direction. You have the up-down direction, and you have the left-right direction. That's why it's called a 2-dimensional plane. If we were dealing in 3 dimensions, you would have an in-out dimension. In-out. And it's very easy to do 2 dimensions on the screen because the screen is 2-dimensional. And he says, well, you know, there are 2 variables here, and they have this relationship. So why don't I associate each of these variables with one of these dimensions over here?
I'm not gonna have a too big of a tangent, but if we have more than 2 variables, then we need to have more planes, which means it becomes multidimensional, which is not easy to visualize, which is matrices, right? Let's come back to the ground and listen to what he's saying.
And by convention, let's make the y variable, which is really the dependent variable. The way we did it, it depends on what x is. Let's put that on the vertical axis. And let's put our independent variable, the one where I just randomly picked values for it to see what y would become, let's put that on the horizontal axis. And it actually was Descartes who came up with a convention of using x's and y's, and we'll see later z's in algebra so extensively as unknown variables, or the variables that you're manipulating. But he says, well, if we think about it this way, if we number these dimensions, so let's say that in the x direction, let's make this right over here. This right over here is -3. Let's make this -2. This is -1. This is 0. Now I'm just numbering the x direction, the left-right direction. Now this is +1. This is +2. And this is +3. And we could do the same in the y direction. So let's see. So this could be, let's say this is -5, -4, -3, negative. Actually, let me do it a little bit neater than that. Let me clean this up a little bit. So let me erase this and extend this down a little bit so I can go all the way down to -5 without making it look too messy. So let's go all the way down here. And so we can number it. This is 1, this is 2, this is 3, and then this could be -1, -2. And these are all just conventions. It could have been labeled the other way. We could have decided to put the X there and the Y there and
Absolutely.
make this the positive direction, make this the negative direction. But this is just a convention that people adopted, starting with Descartes.
It's a convention / abstraction. Down is minus, up is positive, right is positive, and left is not. Wow. It makes you think that we live in a society.
-2, -3, -4, and -5. And he says, well, I think I can associate each of these pairs of values with a point in 2 dimensions. I can take the x coordinate, I can take the x value right over here, and I say, okay, that's -2. That would be right over there along the left-right direction. I'm going to the left because it's negative, and that's associated with -5 in the vertical direction. So I say the y value is -5, and so if I go 2 to the left, 2 to the left, and 5 down, I get to this point right over there. So he says these two values, -2, -5, I can associate it with this point in this plane right over here, in this 2-dimensional plane. So I'll say that point has the coordinates, tells me where to find that point, -2, -5. And these coordinates, they're called Cartesian coordinates, named for Rene Descartes. He's the guy that came up with these. He's associated.
Even the word cartography comes from Descartes? Or, wait, what does cartography? Ooh, ad break. I did not see that. Oh no, ad break comes in 50 seconds. Cool. And I can't snooze it, so we're gonna go there.
All of a sudden these relationships with points on a coordinate plane. And then he says, well, okay, let's do another one. There's this other relationship where I have when x is equal to -1, when x is equal to -1, y is equal to -3. So x is -1, y is -3. That's that point right over there. And the convention is, once again, when you list the coordinates, you list the x coordinate, then the y coordinate. And that's just what people decided to do. -1, -3. That would be that point right over there. And then you have the point when x is 0, y is -1. When x is 0, right over here, which means I don't go to the left or the right, y is -1, which means I go 1 down. So that's that point right over there, 0, -1, right over there. And I could keep doing this. When x is 1, y is 1. When x is 1, y is 1. When x is 2, y is 3. When x is 2, y is 3. Actually, let me do them in that same purple color. When x is 2, y is 3. 2, 3. And then this one right over here in orange was 1, 1. And this is neat by itself. I essentially just sampled possible x's. But
what is... Oh my god, I said we are in an ad break, and here I am watching stuff. No. Ow, sorry. I punched the mic again. Are we in an ad break? How would I know? It's not saying viewers are in an ad break, so I don't know. Oh, there it is. Now it says ad break for 1 minute and 20 seconds. So we have 1 minute, 1 minute and 10-ish seconds that I can put behind me to say technically an ad break. Yeah. Things that I still have yet to be interrupted. Cool. That's great. Oh, hey, we see chat but why now? Huh. Oh, thank you. Let me know when you get it. Yeah, I would appreciate that. So the thing that I changed about chat that now we see, I mean, I changed it when I went to the black void, not now, but it was that I had it be twice the size, so that it was just bigger here, but smaller in the previous scene here. Like this shape works great for this scene, but for this scene, it would be nice if it was like twice the size. And that's all the change that I did. through CSS, but apparently it's not happy about it. Let me see if I still have the CSS copied. I do. Let me try and paste it. Let's go to the black void and do that. Hey, ad break ended. Still. Let's test it. Hello. Go. Hey, see? Why is it working now, huh? Why? Anyway, life is great. Life is lovely. Right. So I'm guessing the next neato thing would be to connect them. And now we have a line.
Realize is not only do you sample these possible x's, but if you just kept sampling x's, if you tried sampling all the x's in between, you would actually end up plotting out a line. So if you were to do every possible
And then you can use it for prediction. What?
x, you would end up getting a line that looks something like that right over there. And any relation, if you pick any x and find any y, it really represents a point on this line. Or another way to think about it, any point on this line represents a solution to this equation.
Right. I mean, yeah, we are going number by number, but if we had gone from, like if we had gone 5, 5, 5, we don't know for sure, right? Like if it's an actual relationship between two numbers, maybe one of them is like the weather. You can't know for sure.
Right over here. So if you have this point right over here, which looks like it's about x is 1.5, y is 2.
Oh, hi, I am back. What's up? Long time no chat. The never world. I am back for the time being. Who knows if I will be gone again? But I had some health issues the past few months, 2 months and a half. Let me self promo. Did I make a video about it? No, I did not. I'm editing a video about it. I've been editing it for almost like, I wouldn't say a week, but I have the video that I need to like. I'm editing it slowly, but I'm editing a video about my why I was gone for over 2 months. It was because I was diagnosed with brucellosis, which, like, what is that? Yes, that was my last stream. That's a VOD on YouTube, I think. I need to stop saying the names of these platforms. Because I think I can reapply for streaming on the Clock app. Maybe tomorrow or today. We'll see. So yeah, hi. We're studying math right now.
So let me write that. 1.5, comma 2. That is a solution to this equation. When x is 1.5, 2 times 1.5 is 3, minus 1 is 2. That is right over there. So all of a sudden, he was able to bridge this gap or this relationship between algebra and geometry. We can now visualize all of the x and y pairs that satisfy this equation right over here.
Okay, yeah, that makes sense. If you have an equation, you can figure out the relationship between numbers, but not if it's real world numbers, right? Oh yeah, I also covered it in a YouTube short. You're right. I should stop saying the names of the platforms. Yes, I have a 1-minute short about it as well. True.
And so he is responsible.
I guess it doesn't contain the treatment and recovery part as extensively because it's, yeah. Oh, thanks. Yeah, that's the name of the thingy.
Responsible for making this bridge. And that's why the coordinates that we use to specify these points are called Cartesian coordinates. And as we'll see, the first type of equations we will study are equations of this form over here. And in a traditional algebra curriculum, they're called linear equations.
Ah.
Linear equations. And you might be saying, well, okay, this is an equation. I see that this is equal to that. But what's so linear about them? What makes them look like a line? And to realize
Exactly. That's the thing. The thing. Like you could draw it in a line and it would work out, right? That's what's linear about them, right?
why they are linear, you have to make this jump that Rene Descartes made. Because if you were to plot this using Cartesian coordinates on a Euclidean plane, you will get a line. And in the future, we'll see that there's other types of equations where you won't get a line. Well, you'll get a curve or something kind of crazy or funky.
Yes. Okay, Cartesian. What? What was the Cartesian thing? In a Euclidean surface. Like that, those words scare me. But I suppose one has to start abstracting some way. So this is why the letters. Abstraction, right? Do I need to go in like 15 minutes? Should I go? Because do I want to go to the next unit and then I'd have to leave early? Lesson. Yeah. Oh, this is a 3-minute. Okay, let's let him talk and then we'll decide.
Jesse Rowe, who's a math teacher at Summit San Jose and a Khan Academy teaching fellow, and you had some interesting ideas or questions.
Yeah, one question that students ask a lot when they start algebra is, why do we need letters? Why can't we just use numbers for everything?
Why letters? So like, why do we have all these X's and Y's and Z's and ABCs when we start dealing with algebra?
Yeah, exactly.
That's interesting. Well, why don't we let people think about that for a second?
Abstraction?
So Sal, how would you answer this question? Why do we need letters in algebra?
So why letters? So there's a couple of ways I'd think about it. One is if you have an unknown. So if I were to write x plus 3 is equal to 10. The reason why we're doing this is we don't know what x is. It's literally an unknown. And so we're going to try to solve for it in some way. But it did not have to be the letter x. We could have literally written blank plus 3 is equal to 10. Or we could have written question mark plus 3 is equal to 10. So it didn't have to be letters, but we needed some type of symbol. It literally could have been smiley face. Smiley face plus 3 is equal to 10. But until you know it,
I would make a confused face just to know it's an unknown. And then each emoji for each thing. Like for y, I don't know.
needed some type of a symbol to represent whatever that number is. Now we can go and solve this equation and then know what that symbol represents. But if we knew it ahead of time, it wouldn't be an unknown. It wouldn't be something that we didn't know. So that's one reason why I would use letters, and where just numbers by itself wouldn't be helpful. The other is when you're describing relationships between numbers. So I could do something like, I could say that whenever you give me, if you give me a 3, I'm going to give you a 4.
Always good to specify if Euclidean or non-Euclidean, like with, say, the length of a vector or distance between points, maybe like you take a taxi cab, to Manhattan, like RMS norm for machine learning is a different non-Euclidean metric. Oh, really? Root, mean, what is the S? Squared, right? RMSE, and then the E is, I think, evaluation. Okay. So one of them is Euclidean. Oh, yeah. What would non-Euclidean mean? Because, like, okay, Euclidean, we can get distance and circumference and stuff. L2 norm is Euclidean. Okay. Is Manhattan? What does Manhattan mean? Hold up, let me Google that. So Euclidean and non-Euclidean. Oh, there's a book of... so Manhattan is a thing. I mean, I just want to see the difference. hey, Google is like, do you need help with with homework? Probably. See, there's an explain to me like I'm 5. I need that. Oof, okay. So piece of paper that's big enough, flat surface, drawing circles and stuff. Non-Euclidean, because it doesn't assume it's a flat surface. Perfect, that's it. I got it. That's all I needed. Yeah. So like, one of them is expecting everything to be like the real world. The other one. So Manhattan is a New York. Thank you. Oh, I get it. Yes, the streets of Manhattan are like a grid. Distance you have to travel along the axis. So it's like a flat surface. So you have the x's and the y's. But the non-Euclidean means it's free for all, basically. That makes sense. Which is easier than the Pythagorean theorem. Yeah, I think I know what you mean. Cool. Sort of. We'll get there when we get there. Which is why I'm taking things slowly.
And I could say, if you give me a 5, I'm going to give you a 6.
Oh, yeah.
And I could keep going on and on forever. If you give...
There are an annoyingly number of probably Facebook posts saying, what's the relationship between these two numbers? And sometimes they make sense, sometimes they don't.
If you give me a 7.1, I'm going to give you an 8.1. And I could keep listing this on and on and on forever. Maybe you could give me any number and I could tell you.
I mean, this is just a +1.
What I'm going to give you, but it would obviously, I'd run out of space and time if I were to list all of them. And we could do that much more, I guess, elegantly if we used letters, if we to describe the relationship. Maybe what you give.
A circle plotted by constant radius from a point is like a diamond in the Manhattan word. Circle plotted by Why diamond? Because it needs... Cool.
Me, we call X, and what I give you, we call Y. And so I say, look, whatever you give me, I'm going to add 1 to it, and that's what I'm going to give back to you.
So it's instead of, going back to his question, instead of writing down every possible thing, you just sum it up in a equation.
And so now this very simple equation here can describe an infinite number of relationships between X, or an infinite number of corresponding Y's and X's. So now someone knows, hey, whatever X you give me 3, I add 1 to it, and I'm going to give you 4. You give me 7.1, I'm going to add 1 to it and give you 8.1. And so there's no more elegant way that you could have done it than using symbols. With that said, I didn't have to use X's and Y's. This is just a convention that kind of comes to us from history. I could have defined what you give me as star, and what I give you as, I don't know, as smiley face. And this also would have been a valid way to express this. So the letters are really just symbols, nothing more.
Nice. Okay, so lesson 1 completed. What is a variable? I think I do want to continue because it's nothing difficult. We've been here for an hour and a half, sort of counting the beginning 10 minutes of like starting. Since it's a Saturday, I do want to like take advantage of the time I have, because midweek I don't always have the same amount of time to stream, and taking advantage of the internet allowing us to stream as well. I do want to continue for another 20 minutes and see just how far we go, basically. And I think we have a quiz coming up. Maybe? We'll see. I don't think... Is it a quiz? Is that a quiz? I see. Hey, what happened to my... Oh wow. This is lesson 1? Okay. Practice, not a quiz. This is a quiz. Oh, no, we won't see a quiz for a while. Okay. So what is a variable? Ask the programmer or the math person.
Let's say that I'm working in a restaurant and I'm making $10 per hour, but on top of my hourly wage, I also get tips each hour. So this entire expression, you can view this as how much I might make in a given hour. Now, you might also realize that the number of tips or the amount of tips I might make in an hour can change dramatically from hour to hour. It can vary. 1 hour, it might be lunchtime, get a lot of tips. People might get some big ticket items. The next hour, I might not have any customers, and then my tips might be really low. So the tips part right over here, we consider that, the entire word, we consider that to be a variable. From scenario to scenario, it can change. So for example, in one scenario, maybe it's lunchtime, I'm getting really big tips. So tips is equal to, let's say it's equal to $30. And so the total amount I might make in that hour is going to, we can go back to this expression right over here. It's going to be 10 plus, instead of writing tips here, I'll write 30 because that's what my tips are in that hour. And so that is going to be equal to, going to be equal to 40. Let me do that. Let me do it in that yellow color. It's going to be equal to $40. But let's say,
so the tips part is the variable and the hourly wage is the constant for the programmers out there.
right after that, the restaurant slows down. We're out of the lunch hour for whatever reason. Maybe the restaurant next door has a big sale or something. And so the next hour, my tips go down dramatically. My tips go down to $5 for that hour. Now I go back to this expression. The total I make is my hourly wage plus the $5 in tips, which is equal to $15. As you see, this entire expression, the 10 plus tips, it changed depending on what the value of the variable tips is. Now, you won't see whole words typically used in algebra as variables. We get lazy, and so instead we tend to use just easier to write symbols. And so in this context, instead of writing tips, maybe we could have just written 10 plus t, where t represents the tips that we get in an hour. And so then we would say, okay, what happens when t is equal to 30? Well, if t is equal to 30, then we'd have, let me write, so what happens when t is equal to 30? Well, then we have a situation, t is equal to 30. This evaluates to 10 plus 30, which would be 40. What would happen if t is equal to 5? Well, then this would evaluate to 10 plus 5, which is equal to 15. Now, I want to be clear. We didn't even have to use t. We didn't even really have to use a letter, although in traditional algebra, you almost do use a letter. We could have written it as 10 plus x, where x is your tips per hour. X might not.
I actually really like those texts. Oh wow, it's a pop-up thingy. Whoa.